Hi guys, good afternoon. Thank you very much for watching. Today's video is going to be my study notes. So as you can see, I have a playlist on my channel for the PIC16F684. These videos are not expertly created. They were created by me, a guy who is trying to learn and develop my programming skills, and I'm trying to learn more about this chip. I'm also following along in a textbook, and believe me, I'm being very careful not to include anything from the text in my videos because I think that's considered plagiarism, so I'm not doing that. But the text I'm reading doesn't always explain things very well, and the author doesn't always explain concepts and ideas presented in the text. So if I really want to get the most out of this particular text, I'm having to look beyond it. So this is a memorandum to myself, and you might even consider it like a companion guide to the certain text I'm reading. So this video I intend to be long. It's going to cover lots of introductory concepts in writing your code in assembly language for this particular chip, and it may not be in any particular order. Now that's 2 minutes of talking. I'm going to get right into a bunch of stuff. Here we go. Thanks for watching, and please check out the playlist because I have lots of other videos on this chip. Alright, so I'm kicking things off with the topic of bank switching. You might know about that already, and I do too, but I would like to really examine it closely to reinforce what I know about bank switching. So here is the data memory map of the PIC16F684, and if I scroll down, it can be seen that there's a bank 0 and a bank 1. And just generally, when you are programming your chip and you need to make use of the different special function registers, which are all the ones with a specific name attached to them, and when you're also using the general purpose registers, which you can write to as just scratch pad memory locations. Again, you'll notice that there are two different banks. So to access these different special function registers and GPRs, you'll have to switch to the required bank to be able to manipulate the data in whatever special function register you're trying to manipulate. So there is a special format of assembly code that is necessary to write to the SFRs in the different banks. So that's what this particular block of code is doing here. It's doing a bit clear F instruction of the status register. It's selecting RP0, which selects bank 0, and it's bit clearing that bit. Before I get too deep into covering this topic of bank switching, to the best of my knowledge, I happen to know that bank switching was something that was rectified in later chips, in newer versions, newer families of the different PIC microchip families. So I believe in the PIC18F family, bank switching and writing applicable code for that is not necessary. And I forget exactly why that's the case, but I just happen to know that. On my channel, I have a fair number of PIC18F videos, and bank switching was not required in programming the 18F chip, but it is necessary in the 16F family of chips. So this is the 16F684 data sheet, and here is the block diagram showing where the status register is. It's in proximity to the file select register, the address mux, the multiplexer on the ALU. So here is the status register, and I can say that on the 18F4525, which is not what this chip is, this RP0 and RP1 bit are not included. Well, that's enough talking about the 18F family. I'm just saying that in different PIC chips, this bank switching bit is not. But it is necessary in the PIC16F684, which is what we're looking at. I won't read all of this, just the beginning. The status register shown in register 2.1 contains the arithmetic status of the ALU, the reset status, and the bank select bits for data memory SRAM. Well, I'll try and stay on topic. We're talking about bank switching. So bit 5 is RP0, which is the register bank select bit used for direct addressing. Set to 1, it equals bank 1. What's this here? Is this the range of file addresses? 80H to FFH. Here's, if it's set to bit 0, it equals bank 0, which is 00H to 7FH. To be emphatic, I'm back here looking at the memory map, and here is the file location or file address of bank 0. It goes from 00H to 7FH. That's bank 0. And file address 80H to FFH is bank 1. So staying on topic, what other bits in the status register are related to bank switching? So what's this bit 6? Bit 6, RP1. This bit is reserved and should be maintained as 0. I don't know why. I came across that before. I haven't sorted that one out yet. I don't know what the IRP is. So, for intents and purposes of what I'm looking at right now for bank switching. In the status register, bit 5, the RP0 bit is the register bank select bit used for direct addressing. So, as I said before, this block of code is used for bank switching, and it precedes virtually every code I've come across on this chip. So bit clear F, status RP0, this will select bank 0. Now, it's showing this RP1 here. It should be maintained as 0. I'll be honest, I'm looking at some sample code. Bit clear F, RP1, well, it's clearing it, so it's also setting it as 0. Okay, so the reason this is cleared, bit clear F status RP1, is because the data sheet says so. So it's maintained as 0 according to data sheet on the topic of the status register. Maybe I will learn why. Maybe, maybe not. According to some research, bank switching is a technique used in microcontrollers with limited addressable memory to extend the accessible memory space. In the context of the PIC16F684 microcontroller, bank switching allows access to more special function registers, SFRs, and general purpose registers, GPRs, than would otherwise be possible with a small address space. Alright, so I found something that might shed light on the bits in the status register. Bank switching example. If RP1 equals 0 and RP0 equals 0, bank 0 is selected. If RP1 equals 0 and RP0 equals 1, bank 1 is selected. And then it's saying if RP1 equals 1 and RP0 is selected, bank 2 is selected. If RP1 is 1 and RP0 is 1, bank 3 is selected. So here I am back at the data memory map, and there are only 2 banks, 0 and 1. So this is perhaps why this bit RP1 is maintained as 0. Okay, my next point will make more sense as I continue explaining it. So port A and port C are in bank 0, and the trace register are in similar spots but in bank 1. The next line of our code, or sample code, is clear F port C. This seems to assume that the ports are going to be output, because to clear F port C is to write zeros to all of them, which is a digital low signal. So all of the port C bits are set to low. And once again, because port C was in bank 0, that's why this was cleared. The RPO bit on the status register was cleared because that gives us access to bank 0, and that's where port C is. Now, to my understanding, the trace register sets GPIO port bits as inputs or outputs, and if we want to access those, that's in this bank 1. Trace A and trace C are in bank 1. So the next part of our code block, bit set F, status RP0. So it's writing a bit, a high, a bit 1 to RP0. when we set RP0, it is selecting bank 1. And it's doing a clear F trice C, so it's writing all zeros to the trice C or tris C register, which is making all the port C GPIO pins as output pins. And to finish off this code block, it's doing a bit clear F status RP0. It's doing the exact same thing that this first line is doing. So it's returning. I should be careful with that. I should be careful with that word return because it means something. But it's sending the selection of bank back to bank 0. And as you can see, this is just a blink sketch, about as simple as you can make it. I can't scroll down any further. There's a delay routine, so it's setting port C, whatever this bit is, bit 5. Most likely that's RC5. So I don't know about you, but I learned something. So that's all I'm going to discuss with bank switching. Alright, I lied. I'm still talking about bank switching. I posed a question earlier on as to why the PIC16F series does not require bank switching in those chips. Why not? Why doesn't it need the same thing that the 16F family needs? 16F needs bank switching. 18F does not. Why? I don't know. But the internet has an answer for me. The PIC18F series microcontrollers, unlike the PIC16F series, have enhanced memory architecture that eliminates the need for manual bank switching. This improvement is due to several architectural enhancements and features present in the PIC18F series. I'll go a little further. The PIC18F has larger and linear memory. The PIC18F series has a larger and more linear memory space compared to the PIC16F series. This allows direct access to a much larger range of memory addresses without the need to switch banks. And 2, access bank feature. The PIC18F series includes an access bank feature which provides direct access to commonly used special function registers and a portion of the general purpose registers without changing banks. The access bank, well, it gets a little more specific. And the 18F has a larger instruction set. It's got a few more instructions. Well, that's an interesting topic. I'll leave it at that. Hopefully I didn't confuse the viewer even more by talking about the 18F series. But I wanted to know that because there is a difference between the two families of chips. So yes, just a warning that this video could be very boring, but it covers a lot. So I asked an internet resource, in PIC programming, what is the MPASM assembler? MPASM, Microchip PIC Assembler, is an assembler tool developed by Microchip Technology for programming PIC peripheral interface controller microcontrollers. It converts assembly language code into machine code, which can then be uploaded to a PIC microcontroller for execution. Here's an overview of MPASM. Assembly language. Assembly language is a low-level programming language that is specific to a particular computer architecture. For PIC microcontrollers, this means using mnemonics and syntax that directly correspond to the machine code instructions understood by the PIC hardware. MPASM assembler. MPASM translates the human readable assembly language, which is what this is, into machine code. This machine code is in a format that the PIC microcontroller can execute directly. The assembler also handles directives, macros, and other features to aid in programming. Development environment. MPASM is often used within development environments like MPLAB X IDE, which is what this software is, which provides a comprehensive suite of tools for PIC microcontroller development, including editing, compiling, debugging, and programming. Functionality. Instruction translation converts assembly instructions into binary machine code. Macro processing supports macros to simplify repetitive code sequences. Direct handling processes assembler directives that control the assembly process. Example, defining constants and reserving memory space. Error checking identifies and reports syntax errors, undefined symbols, and other issues in the assembly code. Listing file generation produces detailed listing files that include the source code, machine code, and memory usage. File outputs. File outputs. Hex files. The primary output is typically an Intel hex file which contains the machine code and is used to program the PIC microcontroller. LST files, listing files that provide a detailed map of the source code to machine code translation. Error files that log any issues encountered during assembly. MPASM is a crucial tool for developers working with PIC microcontrollers as it enables the translation of human-readable code into a format that the microcontroller can execute, facilitating the creation of embedded systems and applications. Alright, well, I've been hearing about macros for a long time. I think I know what that's about, but I could really use a definition. So macro processing in assembly language involves defining sequences of instructions or code snippets that can be reused multiple times throughout the program. A macro is essentially a template that can be expanded into actual code whenever it is invoked. This helps reduce repetitive coding and makes the program easier to manage and read. So to me, a macro is a little bit like a higher language level that's created to do repetitive assembly type instructions. Would you say that too? So I found an internet example. And the example is, suppose you frequently need to toggle a specific bit in a register. You can define a macro to do this. So I found some sample code. Let's try it. I'll just type it out here. Oh, there it goes. So in this example, the toggle bit macro takes two parameters, reg and bit. When invoked, it expands into the BTG instruction that toggles the specified bit in the specified register. How embarrassing. I'm looking at the PIC16F684 instruction set, and I don't see the BTG instruction in any of these categories. Alright, I'm trying this out on screen. I'll just type this out here. Whoops. Okay, so I found some other examples of hopefully 16F instruction set examples of macros. So I'll just read it. Macro to set a bit in the register, set underscore bit macro reg bit BSF reg bit end M. Macro to clear a bit in a register, clear underscore bit macro reg bit BCF reg bit end MM. End M. So I guess this is the format. Maybe it requires this at the end, and I guess you're using repetitive examples to do something. I'm learning this as I'm reading it, so for you experts out there, please don't be hard on me. So basically you could write this instead of this now, although this is almost as simple as this, and this is actually shorter, so this would seemingly make things more complicated. But I suppose you could write out a longer code block that you could still just call this. I better not say more as I'm thinking out loud and learning this. So hopefully that gives you a taste, just the flavor of what a macro is all about. So if you're following along closely, I read a big lengthy explanation as to what the MPASM stuff is all about, and included in that description was the concept of directive handling. So I'll try to define that a little further. Alright, so directive handling. Here's a definition. Directives are commands that give instructions to the assembler itself rather than generating machine code. They are used to control the assembly process, define constants, allocate memory, include files, and more. I guess org and end, which I cut off on the screen, I guess those are directives. I guess the include PIC16F684 dot include, I suppose that's a directive. Okay, it's not contained in this code, but I guess you can define constants, and then when you write your code, well, maybe that's not the best place to put it, you could use that constant that you defined up here. You can just use that value rather than... Well, here's another example code that I'm working on to control a shift register with this chip. This is actually my work. It's a work in progress. But yeah, how was I doing this? So I was defining a term and then assigning it to a port and a particular pin. Just in the internet example, it didn't, say define a port like that. So if you're following along, I'm talking about directive handling, and Directives are commands that give instructions to the assembler itself rather than generating machine code. So I suppose like these instructions are going to generate machine code, but this isn't going to generate machine code. This just tells the assembler how to handle things. They're, dare I say it, they're instructions to the assembler. They're not user assembly code that gets converted into machine code. I forget what the more technical term for this is. I guess these are equates, and this reserves memory location for these, what do you call that? Is that a constant? Or they're like user-defined constants? Equates. I guess those are allocating memory. Allocating memory is another type of directive. And I'm not speculating. I read that in a source. I just needed this on screen to show the example. So allocating memory is another type of directive. Defining variables, that's really what that's doing. And that's a type of directive too. I suppose this is two examples. One directive is allocating memory, and the other is defining variables. It's defining them, and it's also allocating a memory location for them. By using macros and directives, assembly language programming becomes more powerful, flexible, and easier to maintain. Macros allow for code reuse and abstraction, while directives give control over the assembly process and organization of the code.